Okay, so now we are on the forces section of this chapter. And, all right, so forces can sort of cover quite a few things. One of the big ones is gravity. And so this is just showing like something fallen from a building. And Aristotle, who was a philosopher a long time ago, he just said heavier objects would fall faster, which makes sense. And objects moving horizontally require continuously applied force. So if I'm going to push something, across the floor or whatever, if I roll it, it's going to eventually stop. But if I want to just keep going, I got to keep pushing on it. And really, he just kind of did this basically on thinking about it. Then Galileo and Newton came along and they said all objects fall at the same rate. So now it's saying, well, if it's heavier, if one thing's heavier than the other, it's still going to hit the ground at the same time. And if we were in class right now, I'd take a book and I'd take a piece of paper and I'd crumble it up. So if you have these things, or if you just have something that's heavier and lighter in front of you, I would take them in my hand, drop them at the same time, which is kind of hard to do, and they'll hit the ground at the same time. And then they also said no force required for uniform horizontal motion. And then they also based these things on actual experimentation. So those are sort of like some interesting things, from our past that some scientists and philosophers have kind of thought about stuff. We think about stuff, but really, when we want to know something, we need to do an experiment. All right, so forces. Forces are defined as, it won't let me write on it again, a push or a pull on an object. So if you push something, you're applying force. If you're pulling something, you're applying force. The earth pulls on us, right? That's gravitational force that's pulling on us. The overall effect, or this word vector again, which is the sum of the net forces. So like for instance, on picture A here, you've got these two arrows that are both going to the east. Well, if I get the net sum of that, then it's like twice that length, okay, going in the same direction. Picture B here, if I've got one going towards the east and then one going towards the west, if I add those up, it's like basically taking 1 minus 1, which is 0. Okay, so it's just going to stay in place. And then, of course, you've got 1,000 units to the east and 2,000 units to the west. So you could say, 1,000 units to the west, or you could even say negative 1,000, which the negative kind of tells you the direction. So forces can be represented by vectors as well. Okay, and so some fundamental forces that we talk about in physics. One of the biggest, obviously, is gravitational, and that depends on mass and how they interact with each other. And it can also involve things like big, planets, stars, galaxies. We have electromagnetic forces, which is how we have electricity. There's, in our wires inside the walls that you can't see, and you can't even see the electricity that's moving because it's so little. We're talking about atoms and molecules here. But whenever those atoms and molecules move towards each other, they can create electricity. So those forces that are causing, the movement can create that electricity. Number 3, these weak forces. These are involved in nuclear reactions. Weak forces obviously are not going to be as strong as something like number 4, where you are trying to hold nuclei together. We haven't really gotten to the chemistry portion, but You know, let's say I have an atom here and I've got, let's say, some protons in the middle, which we haven't got. You don't have to memorize protons or anything yet. I'm just kind of showing you something really quick. And then let's say that we've got these electrons. Actually, I'm gonna erase that, which it won't let me. What did I just do? Anyway, I'm gonna put these electrons close here, and one's kind of farther away. But do you think that these negatives are kind of attracted to these positives? Absolutely. And that nuclei, that middle section there in the atom, is held together pretty strong. Okay? So those have strong forces. And then we have things like balanced and unbalanced forces. So motion that's going to continue unchanged without an unbalanced force. So like, for instance, if I take a ball and I roll it on the floor, what I said earlier, it stops. Why does it stop? Because there's friction on the ground, there's gravity that's pulling it down, drag, you know, it's maybe getting some air resistance. So there's lots of forces that are kind of, you know, making it stop. But if there was no forces, no gravity, no friction, none of that, would the ball keep going? Yeah, it would continue on and on. Okay? So there are things that are like these retarding forces that are going to cause this decrease of speed. There are also forces that are going to boost the speed. So like when I take my hand and I push that ball, that increased it, right? It boosted its speed from 0 to whatever. And then there can be sideways forces that can even cause there to be like a change in direction. So this is just showing you a satellite that is, you know, experiencing all of these different types of balanced and unbalanced forces. Okay, so now we get to our falling objects, which whenever you think of something that's falling on Earth, it is experiencing gravity, right? So a falling object is under the influence of gravity, and that is known to be in free fall. So if it's in free fall, then you have to involve gravity. And gravity on Earth has a certain amount, okay? And we'll get to that in a minute. And then what I want you to see is that, like, let's say that you were dropping an object off of the top of this building right here. In 1 second, let's look at it like over here. It's kind of the same situation anyway, but I think this one makes a little bit more sense because gravity is 9.8. So let's just say in 1 second, this object falls 9.8 meters per second. And if you look at this one up here, it just says in 1 second, it falls a total distance of 4.9. Okay. Now, if I take 4.9 on my calculator here, and I multiply it, I'm going to end up getting about this 19.6 if I take it and multiply it by this gravity or acceleration rate and multiply it by half. I'm going to see that it's going to go to about 19.6 meters. So it goes from 4.9 meters to 19.6 meters. Is that a bigger increase? So it increased 14.7 meters from its original 4.9 meters in just 1 second. And then in 3 seconds, it goes from 19.6 seconds to 44.1 meters. Okay? And then it just continues to increase. Well, the same thing, if you go here to this second one, it goes 9.8, and then it's just doubling basically its speed. Okay? you can see. So we've got basically you can find your final velocity here whenever you look at it in this view. All right. So whenever you have an object that's in free fall, you're going to want to involve gravity. Whenever you go to do an example. I think there is an example in the book. Let me pull that up really quick. For some reason, I feel like it's in this horizontal motion. Nope. It kind of, oh, there's the free fall section. Okay. So kind of the same pictures that we've already had. I'm going to take that off of there, and I'm going to show you this example 2.7. So if I were you, I would get out the PowerPoint, just kind of write this over to the side. So this is saying that a rock that's dropped into a well hits the water in 3 seconds. Ignoring air resistance, how far is it to the water? Okay. So this is, sorry, I'm having technical difficulties. Okay, so here's our new equation. Okay, this is free fall. So anytime you see a problem that something is being dropped, you're going to want to look at this problem or this equation right here. So this says that a rock is dropped into a well and it hits the water in 3 seconds. Ignoring air resistance, how far is it to the water? So it's wanting to know the distance. All right, well, it only gave us 3 seconds. So what's A? It didn't tell us the acceleration. All right, so the acceleration is the same thing as gravity, and gravity on Earth, for the most part, the average gravity is 9.8 meters per second squared. Okay, so you would take 1/2 times 9.8 meters per second squared times 3 seconds squared. And you remember PEMDAS, or your order of operations. Some of you are like, I don't know what you're talking about here. This is like if something is in, I can't write down. That's so hard. Yeah, I'll write kind of like to the side here. This is like parentheses. This is exponents, multiplication, division, addition, and subtraction. So do I have parentheses? It's kind of a trick question. I do have parentheses, but I put parentheses sometimes around one thing, like 9.8 meters per second squared, just to make it look a little bit prettier. If I had 2 things inside a parentheses, then I'd want to do it first. Okay? Do I have exponent? Yes, I have this squared. So you want to do it first. You want to do 3 squared and then kind of go backwards. So do 3 squared times 9.8, then times 1/2 on your calculator. And then you should be good with your number. Otherwise, you can get messed up if you don't put it into your calculator correctly. And it won't end up giving you the right number. Okay. This is showing you that you could also find it by doing sort of our previous equation, where you had this average is equal to final plus initial divided by 2, and then plugging it in like this. So, you know, you could kind of go through and see what you had that way too. Okay, but you'd have to find the final velocity first. And in order to find the final velocity, you'd have to use, you know, this equation from before as well. So that gets a little bit more complicated. But this is how this equation right here was determined, by doing a breakdown of these. All right. So anyway, if you see a problem that is in free fall, you're going to want to use this distance is equal to 1/2 AT squared. All right, I'm going to stop it and we'll start.